going to talk about is classifying decision rules which admit learnability. Right, so it's like in infra-Bayesianism we have the maximin decision rule, and then we can ask the question, what are decision rules we could go with? And an interesting observation is that learnability seems to be, like the learnability of some natural hypothesis process seems like a very strong constraint on the type of decision rules you could go for. Such that maybe in some sense they all can be reduced to the maximin decision rules, but I don't know. So how do we formalize decision rules? Right? What does it mean to have a decision rule? So, for example, we could have some kind of, okay, so let's recall that if we have lambda a law, right, and we have phi a policy, then we can kind of put them together and get this thing, which is an element of box A times omega. Right? So now about this thing, we can have some preferences. And the kind of preference we considered was that there is some utility function. We kind of considered this type of preference where we have like a utility function, which is like a kind of continuous function, whatever, and like the way, and given a critical set, we just look at the minimum over this critical set of the expected utility, and this is our way to define the preference, where this is big or small. But we could also look at some other, where we could have some kind of thing, which is some kind of a mapping from box A times omega to R, for example, which I kind of call it a kind of the hyper utility, for lack of a better name. But when we denote it, yeah. Let's imagine we have some mapping like this, which is something that nothing is formed, and then we use this to compare the critical sets. Or we could even directly just talk about like partial order of the critical set or something. But let's for now stick with this kind of mapping. That's already pretty general. And given a thing like this, we can talk about learnability. Like we can say if we have some hypothesis plus H, we can ask, is there a family of policies? Right, but this also has to depend on gamma in some way, otherwise what it means to talk about learnability, right? Mm-hmm. So is there a family of policies such that, so just like for every H, like if we like take H and apply gamma and apply our anti-gamma to this, and we take the limit, and we see how much worse this is compared to the best we could get. So we look like it, look at like maximum over pi of anti-gamma, H by gamma minus anti-gamma, H prime minus anti-gamma H by gamma, and then say that the limit is gamma goes to 1, maybe we want it to be 0, right? Okay, but this is, we still have this kind of gamma dependence here, which is like not clear, it's kind of very general, like not a lot of unity to get a gamma dependence. So we need to do something about this gamma dependence. One natural approach is, okay, let's suppose that this thing factors from some state representation, like a reward function. But recall that the natural way to think of rewards was we had a reward machine, right? So there was like some S0, and there was some T from S0 times A times O to S0, and then we assign kind of reward to every state here, right? Or maybe to every state action. Right, and this was like a way to specify, and way for parties communicating, this was a way to specify rewards. But now suppose that we have this T here, and it is good like communicating, maybe it's probably want to communicating, right? In the sense that like we assign here. So we have this communicating T, and this allows us to get a mapping from A times O omega. So first of all, we get a mapping from A times O omega to S omega. Right? What's the sequence of status? This is like this, phi omega or whatever we call it. But then we can also go from S omega to delta S by a mapping which we can call G gamma. So what is G gamma? So G gamma is like, so G gamma applied to some D is a probability distribution over S, and this probability distribution is, so what we do is just think of having 1 minus gamma, 1 minus gamma gamma, 1 minus gamma gamma squared. So this thing is a probability distribution on N. Right? This is like something in delta N. It's just the geometric distribution on the natural numbers. So if we choose a natural number randomly from the geometric distribution, and then we look at state number under this number, so we get like some distribution of the states. Right. So what we got from all of this is we got some phi gamma, which is a mapping from destinies of infinite sequences. This is S0 to distributions over 0. So now, so now suppose that this eta, instead of what we have here, eta is now defined on box X as 0. Okay, so we have some way to compare Quidel sets on S0. And now we can do we can rewrite this condition. So we can say there exists some gamma, essentially for any hypothesis, limit as gamma goes to 1 of max pi of eta of of what? So eta of taking phi gamma and pushing with it h pi, right? Minus eta of again phi gamma pushing with h pi gamma, and this limit equals to 0. So now we define what does it mean to be learnable with respect to such a hyperutility function, something that just takes Queen sets as input. So now it's not, doesn't have to be worst case, could be best case, median case, could be anything you imagine. But how easy is it now to get learnability? Right? And then you can ask the question for a given eta is, for example, the class of resettable infra-RDPs, eta learnable, for example. And this turns out to be a really strong condition of eta. So strong that currently I only know one type of, okay, now two types of examples which satisfy it. So one type of example is any eta that's monotonically increasing. So for eta that's monotonically increasing, that's going to work. So this means the more ambiguity, the better. So the more ambiguity, the better has the property that it's equivalent to kind of assuming in some sense that the environment is cooperating with you. The kind of nature is choosing the best possible distribution out of the critical set. And that's why it's pretty easy to come up with learning algorithms here to deal with ambiguity, because the ambiguity is just working out to the way you want to work out. But this seems like not a very interesting decision rule. And the second example is eta of theta is some kind of is something like t times minimum over this thing of the expected value of some reward function plus 1 minus t maximum. Reward function, where r is just some reward function and t is some number between 0 and 1. So this thing is kind of interpolates between the maximum decision rule and the maximus, like interpolation between pessimism and optimism. But in some sense, it can also be usually kind of reduced to just maximin, because we can always have like a short form that kind of explains it. We can always take the best case and put it as a separate hypothesis into our hypothesis class, and then learning this new class, kind of instead of saying we're learning this mixed kind of decision rule thing, we're just learning the ordinary maximum decision rule, but in an extended hypothesis class, which also has like the best case.
Why can't you pull the same trick with the monotonically increasing case?
You can, basically.
Okay. So why is the monotonically increasing case distinct from just case 2 with t equals 0?
I mean, they're not I mean, technically it's different, right? Because monotonically increasing, but it doesn't have to have this precise form.
Okay, got it.
But in some sense, both of those cases can be reduced to just the ordinary maximum decision rule by changing your hypothesis class. So is there some decision rule which cannot be reduced, but which does satisfy learnability? I don't know. It seems like a very interesting question.